So these are certain things that we need to know about gases. We know that they're going to be compressible. Compressible basically means that we can push them down together, right? And so we can make the pressure greater by pushing them down, you know. We can also, gases are expandable, right? So then they can expand things as well. And so that's kind of shown in the figures down here. Compressible, here we add a little more weight, we can compress the gas. Here we remove the weight, then it's able to expand. And then this can happen at a particular level as well too, right? So here, if we take a look, um, so we have gases that can be at low densities, and we can have gases that can be at high densities. Now, gases at low densities have characteristics of the ideal gas law. Typically, when they're at very high densities, that's when we get into those issues where they're too compact and they're interacting with each other. Gases can be mixed in a fixed volume. So I can put oxygen and hydrogen in the same in the same vessel, and then unless we add something to cause them to react, they won't react. Uh, Gases can exert constant pressure on the walls of the container in a uniform direction. That basically means that these gas particles, they're pushing against the walls even, right, in all directions. So low density gases. So here's an example of a low density gas where we have water, which is high density, higher, and we have a solid, which is even higher in density. And so those low density are going to be able to float on top of water. So we're able to mix gases. So here's an example of us mixing gases. So we have three of the red gases, and then here we have three of the red gases, and three of the green gases. Now, when we add these two, right, when we're talking about the gases, we're talking about quantity, right? So then we have a total of six gases in here where we only have three gases in here. Okay. And so that's going to impact how pressure is going to behave, right? The more quantity that you have, the higher the pressure is going to go up, right? Because pressure and the number of moles are directly proportional. Let's look at that equation. PV equals nRT. And R, where again, N is the number of moles. V is volume. P is temperature. Let me just say absolute temperature. P is pressure. And R is the ideal gas constant. Which we know has a value of 0.0821, and that's ATM liters divided by moles Kelvin. And sometimes you'll use a minus one, like we'll use a minus one on moles for the superscript. And in that case, that just means it's being divided by. If we use the minus one as an exponent. Okay. 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 This here just basically shows us that when we're talking about gases, gases are going to be pushing pressure uniformly. So in all directions, where that's not necessarily going to be the case. It just depends on the depth of the liquid for liquid cases. So it depends on how deep the liquid is how the pressure is going to be behaving. So we talked about the kinetic molecular theory in the very first chapter. Uh, we talked about molecules are always moving. Um, and so that's the thing that we need to remember that molecules are going to always be moving. So gas molecules are always moving. They're going to be moving faster than the liquid molecules, which are going to be moving faster than the solid molecules. And so the average kinetic energy of a gas molecule is going to be proportional to the temperature. So as the temperature goes up, the average kinetic energy is going to go up. So it's going to be directly proportional to the temperature. So here we have steam. And in this case, steam is going to be occupying this whole space. So it's going to represent these little circles are going to be little circles that we're moving along the area um, in the liquid media, right? And so they're going to be roughly about the same number of molecules. Where a gas, you're not going to have that case, right? Gases are going to be mostly empty space. They're going to occupy mostly empty space. When it's a liquid, they're going to be closer together. They're not going to occupy mostly empty space. So often what we do is we take the force over the area, and that's going to equal our pressure. So how much force over a given area of space, that's going to represent the pressure that we're generating. And then factors that can affect your pressure is going to be volume. It's going to be the amount of gas, so your quantity, your number of moles, and it's also going to be your temperature. So if we have an elephant and an ice skater, and they're both on a layer of ice, who is going to have more force on the ice, the elephant or the ice skater?
The elephant.
The elephant.
Tony?
Sorry?
So which one is going to have more force, the elephant or the ice skater?
Oh, the elephant.
Is it the elephant? Okay, so let's go back to that. So if force is going to be equal to pressure over the area, right? So we know that the area that a elephant foot is going to be much bigger. This value is going to be huge compared to our force value, right? So then that means that our pressure is going to actually drop down and be smaller because we're dividing by a larger area in the case of the elephant. In the case of the ice skater, his foot is like what, 5? I mean, I'm probably being too mean, but he's probably like nine. He wears probably a 9 in shoes, right? So really tiny. So if we compare his foot, elephant's foot like this, right? His foot is going to be like this, right? So the elephant is going to take up so much more area. And so the overall pressure is going to be less on the ice because the area of the elephant's foot compared to that of the ice skater. And we also think about that ice skater. He's usually stopping on his tippy toes, right? On the tip of his ice skates. So it's even smaller. So the answer is the ice skater. So this is called a mercury barometer, and basically atmospheric pressure pushes against the mercury, and then it pushes the mercury up into the column itself. And so if it's atmospheric pressure, which is 760 millimeters of mercury, right? And so that's the value of 1 atmosphere. So 1 atmosphere is always equal to 760 millimeters of mercury. So this is just showing you some of the properties of gases. So we know that pressure is going to be equal to the force divided by the area. We know that the volume, which is three-dimensional space that's being occupied by the gas, that's going to be inversely proportional to the pressure. So as pressure goes up, the volume is going to go down. We know that the number of gas molecules in a sample, as pressure goes up, the number of molecules goes up, so your number of moles are going to go up. And as pressure goes up, our temperature is going to go up. And you just kind of think about in a very crowded nightclub, what happens? Everybody start getting hot. You guys are gonna say, "I've never been to a nightclub. I don't know about those things," right? Okay.
Oh, it gets hot.
Okay, so a common unit that we use in pressure is atmosphere. So 1 atmosphere is equal to 760 millimeters of mercury. 1 atmosphere is equal to 760 torrs, which is also equal to 760 millimeters of mercury. And then 1 atmosphere is equal to 101,325 pascals. Pascals is the SI unit that is commonly used for pressure. And if you guys remember in terms of energy, it also tends to represent energy as well. Come on. 1 bar is going to be equal to 100 kilopascals, or just 100,000 pascals. 1 atmosphere is equal to 29.92 inches of mercury, and 1 atmosphere is equal to 14.7 pounds per square inch. We're familiar with the pounds per square inch because that's what we measure the pressure of our tires in. Okay, so if we take a look at the pressure measurement, we have what we call an open-ended manifold. And I'll show you what that looks like here in a minute. In that case, we're going to take what we call the gauge pressure and the absolute pressure. And then I'll tell you what they mean, okay? So if we look at the pressure here, our P gauge, our gauge pressure, is going to be the atmosphere that's going to be associated with the bottle, right? Plus how much the millimeters of mercury that we're changing as well, right? And so we're going to add those two together, and that's going to give my pressure. So that basically means that the pressure inside the flask is greater than the pressure of the atmosphere. PA is representing the atmosphere. Okay? So so if we sit there and we look at it, so this overall pressure is going to be the pressure that's in the gas plus those millimeters of mercury. Okay? Or I'm sorry, millimeters of mercury and the atmosphere, because we know that it's pushing out, it's greater than the atmosphere. So we're going to add the atmosphere plus the millimeters of mercury. That's going to equal our gauge pressure. Now, in the case where the millimeters of mercury are pushing in the other way, that basically means that the atmospheric pressure is greater than the pressure that's inside the bottle. So then that basically means that we take our gauge pressure, and that's just going to be equal to our atmospheric pressure minus our millimeters of mercury, which is just shown right up here. Sorry. Come on. So The pressure inside a steam bottle is 1,427 psi. Express the pressure in atmospheres. So how would I do that? What's my given?
Is it the 1427 PSI?
That's right. So we know we have 1427 psi. Okay. And then how many psi is equal to an atmosphere?
The one?
So one atmosphere is equal to how many psi? It was that page that was 3 pages ago. Or you can look in your.
Give me a second. I can't find it. Give me a second.
Let's see if we can find it together. Oops, wrong way. Sorry. Oops, there we go. So one atmosphere is equal to 14.70 psi. And on the exam, those are going to be given to you if they're having you convert like that.
Okay.
So you just need to know where to put it. What do you guys end up with?
One 100.
Okay.
So is it 14.27 or 14.70?
Sorry, 14.70, my bad. Sorry, my brain is not working.
Okay, let me see what I get. So I got 97.0748.299.
So we had 4 sig figs. So it's 97.07. And you said 299.
48299.
So that would be a 4 here. So we don't have to round it up. So then we'll just have ATM here. So 4 sig figs. Okay. So let's see. Clearance. So the pressure in the automotive tire is 29 psi on the day. The weather report states that the barometric pressure is 30.09 inches of mercury. How would you report the absolute pressure in the tire to a colleague in kilopascals?
So would we start off with the 29 PSI?
Okay. Okay. And we're going to want to do with, what do we want to do with that?
Well, we're gonna want to get the that KPA.
Okay. So we know that our PSI is going to be equal to 14.7 PSI per atmosphere. Because that's what we had last time for ATM. Check it so that I don't make another mistake. And we know that 1 atmosphere is equal to 101.325 kilopascals. So atmospheres are going to cancel out. Pascals are going to cancel out. Then we're going to end up with
Is it 199.89, 2857?
okay. Okay, let's see. So we have two same things. So if it's 199, we can get away with calling it 87, right? KPA.
89?
No, 89. Okay, so then that's going to be 2.0 times 10 to the second power. So then we have two sig figs here. Okay. And then we have our 30.09 inches of mercury. So do we have a conversion factor? I can't remember. Is our inches? Oops, sorry, wrong one. 29.92. It's going to equal 1 atmosphere. So let me write that down because I'm struggling today. So And we know that that's going to equal an atmosphere, which we also know that 1 atmosphere is going to equal 10.1 times 3.25 kilopascals.
So it's going to be 101.90071.
You said 101.
101.90071.
Okay, so we have 4 sig figs. So 101.9 kilopascals. Okay. So let's go to the problem. So they want the absolute pressure. So then that's going to be the pressure of the tire and then the atmosphere, because it's going to have a little more pressure because of the tire. So we're going to add the 2 together. So we have the 2.0 times 10 to the second power and the 101.9. And then that's going to give us 3.0 times 10 to the second power. And that's because they asked us for the absolute temperature. Okay. Okay. So here we're looking at the height of a thermometer, right? And so in this case, we're looking at the volume, right? The volume that's going to be occupied by the thermometer. So as the temperature goes up, the volume is going to go up. So they're going to be directly proportional to each other. And so that allows us to use a thermometer. So since we know that they're directly proportional to each other. How many of you guys are taking your kids' temperature during cold and flu season? Yeah. So so we've already talked about absolute temperature or absolute zero. So we know that 0 Kelvin is going to be equal to minus 273.15, or it's going to be equal to negative 459.67 Fahrenheit. This is when molecules stop completely. They stop moving completely. So that's the reason why we call it absolute zero. So here, so this is basically looking at Charles' law. Charles' law is comparing the volume to our temperature. And there's all of these gas law, but if you remember PV equals nRT, you can get to all of them. So here, we're just saying that volume is directly proportional to temperature. So if we set it equal to a constant, that can make them equal to each other. So our constant is going to be equal to volume over temperature. So we can say our V1 over our T1 is going to equal a constant. And then our V2 over T2 is going to equal another constant. And we can set these guys equal to each other. And we can end up with this equation, right? And that's, again, called Charles' law. So if you're so concerned about the name of the law, just be able to utilize this V1 T1 equals V2 T2. And that's assuming that the number of moles are constant and the number of pressure, the pressure is constant. So if we have those two things being fixed, they're not changing. So then you're going to end up with just that using that equation. Okay, so now let's go ahead and just use this. So it says a container with a flexible wall holds a gas that is cooled from 65 degrees Celsius to 22 degrees Celsius. If the container volume was initially 4.5 liters, what is the volume after being cooled? So we know that T1 is going to be equal to 65 degrees. But we also know that we need to 55 degrees Celsius. We also know that we need to change it to absolute temperature. So that means that we need to add what to make it Kelvin?
Is it the 273.15?
That's right. So if you just remember 273, you're going to be okay. So we're just going to go ahead and use the 273 and then add that together. So what is that? 338 Kelvin. Then our T2 is going to be 22 degrees Celsius. And we're going to add that same value. Okay, and we know that we had V1 over T1 is equal to V2 over T2. And we want to solve for our V2, right? So because we know V1 was 4.5 liters. So we get V2 is equal to V1 over T1, and then we have T2 on top. So we have 4.5 liters times 295 Kelvin, and we're dividing it by 338 Kelvin.
So is it 3.92751479?
So we need two sig figs.
So would it be the 3.9?
Is that 3.9 or 3.2?
3.9.
3.9. Okay. 3.92, right? So yes, it would be 3.92. Sure. Good job. Piece of cake so far?
So far, but when the test comes, I feel like I get stuck.
Yeah. So again, a lot
Is
of
that
times the
because there's so
equations,
many equations we use? That's why
yeah,
we get confused. But
yeah, a lot of times the equations are going to be given to you in the problem. So kind of pay attention to that. See what you have available to use.
But then again, you said that the final is gonna have all the questions are multiple choice, right?
That's right. And also think about it. It's like, so as temperature goes up, we expect the volume to also goes up. As temperature goes down, we expect the volume to also go down, right? Because they're directly proportional. And that kind of helps as well, because then you can eliminate the ones that are high values immediately. Okay. Boyle's law is looking at pressure versus volume. So pressure and volume are indirectly proportional to each other. So let me show you. Ew. I am so cold.
Did you get tested for the flu and COVID too?
Yeah, yeah, I tested, but it was still relatively early. So let me test. I should probably test again, but I tested for COVID, and then I tested for the flu, and my body aches. And they said that I wasn't positive, so it also could be that it's just early.
Yeah, because they told my husband, my daughter, the oldest, she tested positive for the flu, and then
Uh,
we had the same symptoms. Well, we all had the same symptoms, and
yeah,
then came back negative, and then they told him, well, we're just gonna assume that yours is a false negative because you have the same symptoms.
okay,
Because
yeah,
and you're
yeah,
cold because you probably have a fever.
yeah,
yeah, yeah,
my bones hurt, my legs hurt, like even in
yeah,
bed, it was horrible.
yeah, yeah. Everything hurts right now. Everything, my back, my legs. I feel like somebody's just punching the crap out of my legs. Yeah, yeah. I'm the biggest baby when I'm sick, if you can't tell.
I think all men are because my husband was the same way. He stayed in bed.
We were just talking about this over the weekend that men are
Mhm.
big babies.
Yeah. Okay. So if we look at volume, volume is going to be inversely proportional. So basically, volume is going to be proportional to 1 over the pressure. So as volume goes up, pressure is going to go down. Okay. So if we make this a constant, that allows us to set it equal to each other. And so we can use this equation here. And then we can set those two equations equal to each other. So P1 times V1 equals P2 times V2. Now the beauty is that since volume and pressure, when we do the conversion, we don't have to add something. We just have to multiply something. So whatever unit that we're using, we can get away with using that same unit and get that answer if we end up with that same volume, right? So what do I mean by that? So if we had a gas sample occupying 5.818 liters at 776 torr, find the volume of the gas if the pressure changes to 827 torr. So we can use that equation. We have V1 equals P2 V2 and so in that case, we're going to have our P1 is going to be 760 torrs. Sorry, 776 torrs, sorry. And then our P2 is going to be 827 torr. So our V1 starting volume is going to be 5.18 liters. And we want to calculate our V2. So we're going to solve our equation for our V2. So then we get V2 is going to be equal to P1 over V1 divided by P2. And then we just plug things in. So 776 torr divided by 827 torr. So we'll see, of course, cancel each other out. So we don't have to worry about that unit. And then we multiply that by that volume, which is 5.18. So I should end up with 3 sig figs if I'm correct. And then the units that are left are liters. So we expect a volume that is greater than or less than. So pressure is going from a lower volume to a higher pressure, a lower pressure to a higher pressure. So we'd expect the volume to be what? If it's inversely.
Would it be higher?
Okay, so let's plug it in and check. What did you end up with?
4.860555623.
So we should have 3 sig figs. So we said 4.86 liters. So as pressure went up, volume went down. So they're inverse proportional, right? And so that's what we're expecting. Because they're on the same side as each other, so these ones and ones are on the same side of each other, they're always going to be inversely proportional to each other so that they can remain constant. So if this guy goes up in value, then that guy has to come down in value to compensate, right? Or vice versa. when we see that the ones and the ones are multiplied by each other, right? We know that that's going to be inversely. If they're on opposite sides of the equation or they're being divided by each other, let's say as we had pressure over temperature, right? So that would be okay. So these are all the different gas laws, right? And at the end of the day, they all end up adding up to the ideal gas law. Let me erase this here so you guys can see. At the end of the day, they always end up adding to the ideal gas law, right? Or what we call the combination gas law, adding them all up. So this is the combination law. And then we get into, we're not going to do this problem, but it works the same way. You just set everything equal and you need to change your temperature, absolute temperature. Okay. So when we talk about standard temperature and pressure, STP, we basically mean that it's a condition where the temperature is going to be equal to 0 degrees Celsius and the pressure is going to be equal to a bar. Sometimes people will say it's equal to an atmosphere because they're really close in value. A bar and 1 atmosphere are really close in value. So you'll see them interchanged, but really it should be a bar. Remember that. So really it should be a bar. Okay. So the volume of a sample of nitrogen gas is measured at 3.62 liters. When it's at 0.843 bars and 16 degrees Celsius. What is the volume what is the STP volume of the nitrogen gas sample? So what was STP again?
I don't remember.
Okay, so let's go ahead and plug everything in. So we know that pressure P1 is going to be 0.843 bars. T1 is going to be 16 degrees Celsius, but we need to do what to that?
Kelvin?
We need to add what to it?
273.
We're going to add 273 to it, right? To change it to Kelvin. That's right. Is that
Can
what
you
you
guys
said?
hear me or no?
I thought you said change it to Kelvin. Did you say change it to Kelvin?
Yeah, isn't that when you added 273.15?
Yeah.
Oh.
Yeah, you don't have to worry about the 1.5, especially on the exam, you can round. So then that's what, 289 Kelvin. And then we know that our T2 is going to be at STP. So what is that? Is it at 0 degrees Celsius? Plus 273. Plus 273. our V1 is going to be 3.62 liters. And then our pressure, our P2, is going to be, what is it at STP? Isn't it 1 bar? And then, so our V2, we need to calculate. So we know that P1 times V1 is going to be over T1 is going to be equal to P2 times V2 over T2. And then we're going to solve for V2. So we're going to say V2 is going to be equal to P1 over P2 and then we'll have T1 at the bottom here, and we'll have T2 at the top here, and we'll have, and then all we have to do is plug everything in. So we get V2 is going to be equal to 0.843 bar times our T2, which is 273 Kelvin, times our V1, which is 3.62. Then we're going to divide that by 1 bar times our T2, which is T1, which is 289 Kelvin. So our Kelvins are going to cancel out, the bars are going to cancel out, and we're going to be left with just volume. Our V is going to be equal to sharing up 3 sig figs. So 2.88 liters.
Is it 2.88 or is it 288 liters?
It's 2.88. This is a decimal point right here. Right here, that's a decimal point.
Okay.
Yeah, sometimes when I draw it, they don't show up well. Okay. So Anton's law basically says that pressure is going to be directly proportional to temperature. So as pressure goes up, temperatures go up. And so we can make those same insinuations. Avogadro's law is looking at pressure and the number of particles, so pressure and volume. So then you can sit there and directly correlate the volume to the number of molecules that you have. So this is basically showing Avogadro's law. So if we only have a few molecules, you're not going to have too much that's going to be pushing your volume up. The more molecules you have, the more you're going to get pushing. The more, even more molecules you're going to have, you're going to get even more pushing. And so these are all of the different laws, right? And so that's how we end up with the ideal gas law. That's why I started off with the ideal gas law, because we always end up here. PV equals nRT. Perfect. Don't be a permanent. Okay. And so that constant is R. It's the ideal gas constant. We have a value for it. And so here's the ideal gas law. This is just showing you that we can end up with all of the different gas laws if we set certain things fixed or constant. So if we set volume, if we set a number of moles and temperature fixed, we end up with Boyle's law. If we set number of moles and pressure fixed, we end up with Charles' law. If we set pressure and temperature fixed, we end up with Avogadro's law. So from our ideal gas law, we can end up deriving all of our different gases. So I'm not going to have you guys do that one. And I'm actually not going to have you guys do this one either. Although, no, let's talk about this briefly. So we know that N represents the number of moles. So then that basically means for us to calculate the number of moles, we're going to take the mass divided by the mole mass. And that's going to give us a value for N. So we can substitute our mass divided by our molar mass. And then that's going to give us our number of moles. And so we can substitute that in our equation, and we can modify it to sit there and do calculations based upon mass, right? And then we just have to calculate our molar mass, okay? Okay, so what is the pressure, ATM, in a helium-filled 0.77 liter balloon if it contains 1.0 grams of gas at 22 degrees Celsius? So the first thing that we should probably do is to do what? So we know we're going to be using pervenert, right? PV equals nRT. But we know that we have mass. So since we know that we have mass, we're going to substitute N for mass, which is M, over molar mass, which is capital M, capital M. What is the molar mass of helium? So I can just simply just plug it in. So we want to solve for our P. So we get P is equal to mass over MM. And we're going to put volume down here too. RT. Okay, so we know that mass is equal to what? Based upon what the problem says. We have a mass in there. Anything that's grams or pounds or ounces or
1.0.
okay, so we know that it's 1.0. And that's helium. Chemical formula for helium.
Ag.
Okay. So then what is the molar mass of helium?
4.0026.
So we know it's 4.0026. And that's grams per mole. Of helium. Okay. We know that R, I'm going to give you R's value again. It's going to be given to you on the test. It's 0.0821, and that's atmospheres, liters, moles to the -1. And you'll see it written this way on your exam, which means the same thing as divided by moles. And T to the -1, which means, again, same thing as divided by T. Okay, so then we have T is going to be equal to 22 degrees C. Can I leave it like this? Nope, I can't. So I need to add what to it?
273.
273. Then that's going to give us our Kelvin. So then that's what, 295. So then we just plug that into our equation. So we get P is going to be equal to 1 gram times 0.0821, and that's ATM, liters, moles to the -1, and T to the -1. And then we have times our T. So we got, oops, sorry, not T to the -1, Kelvin to the -1. My bad. It's probably where you guys look at me like I'm crazy. Kelvin T. It's too generic. That's 295 Kelvin. So that's Kelvin technically to the +1. This is to the -1, so it's going to cancel each other out. And then here we have molar mass, which is 4.0029 or 26, and that's grams. And so we could say grams to technically the -1 moles. So then that's going to cancel that out. And that's going to cancel out your grams. I don't know where I put that C there for. Oh, that's a 6. That's not a C. 6. So grams are going to cancel out. That's 0. Sorry. As I said, my brain isn't functioning appropriately. So we need the volume. We had our volume, which I didn't put up here. Volume is going to be equal to 0.77 liters. So 0.77 liters. Okay, so what do you guys end up with? So we should end up with how many sig figs? Lowest number?
Is it 7.858?
So if it's 2 sig figs, 7.9. Oops. ATM. Okay. Good job. Okay. Are you guys okay if we stop here?
Yeah, that's fine.